Okay, so this is 4.3, day number 1 and 2. This is day number 1 and 2. I want to look at a function. I'm going to call it f of x. I'm going to put those on the next slide here. For those of you at home, they're just all of a sudden going to appear. Okay, those of you at home, we created a function. We called it f of x. We have the following x values, -3 all the way over to 3, and the following output, 72, 1, -174, undefined, also could be called does not exist, 1/2, 42, and 0. Okay, those are all made up. This is not a function that you will have typically, but let's see what happens with it. So what would happen if I take the absolute value of f of x, the entire function? Well, that takes all outputs and does what to them? Makes them positive. So if they're already positive, keeps them the same. All right, does anything change with an undefined value? No. The absolute value of an undefined value is still undefined, or does not exist. But this value, this 174, that -174 becomes +174. So graphically, what does that mean? Yeah, any value that's below the x-axis now gets flipped, reflected upward. Reflected upward. Okay, cool. That one's pretty straightforward and typically is the easiest to understand. Okay, now what's going to happen? I have f of the absolute value of x. So what's that going to do? The x becomes the opposite. So let's just talk about the ones that are unaffected. Will 0 be affected by this? No. So there will still be an undefined value there. Does not exist. That's terrible, but that says it does not exist. Will 1 change if I plug in a 1? 1 still gives me an output of 1/2. Right? 2 doesn't change, gives me an output of 42, and 3 doesn't change because it's positive, so it gives me an output of 0. But what does -3 become when I plug it in? +3. Therefore, its output is 0. -2 becomes +2, which gives me an output of 42. And -1 becomes +1, which gives me an output of 1/2. So look at that. It turns it into this even function, right? That's symmetrical across the y-axis. So it basically just says, if you're negative, forget the output you have. I'm turning you positive, and then your output is going to be the same as that value. All right? Okay, now let's talk about this 1 over f of x, the reciprocal. Okay, so what's 1 over 72? Well, it's 1 over 72. So it takes a very large number and makes it very, very small. Right? It takes a small number, like let's say 1/2 over here. If I take 1 over 1/2, what do I get? 2. What about 1 over 42? Well, that's a really small number now. So the output that was 42 is now a very small output. So basically, I'm just taking the reciprocal of all of these values. What's the one number whose reciprocal is itself? 1. That's what I like to call the turning point, right? 1 over -174 is a really small negative number. 1 over 0, uh-oh. What happens here? That becomes undefined, so it does not exist. Whereas 1 over undefined becomes, okay, careful here, 1 over 0, right, becomes 1 times 0. Instead of dividing by a fraction, multiply by its reciprocal. So if I multiply by its reciprocal, I get 0. Oh my goodness. You're going to see what happens there as we graph these. Okay. This slide is something cool. It's called the golden ratio. We can talk about that later. We don't have time for that today. This is kind of finishing out the golden ratio. We can talk about that more later. Here's the absolute value of x, right? So if I look at y equals x, I get a straight line with a slope of 1. Okay? Here's my graphical representation. But the moment I take my outputs and I put an absolute value around them, it takes anything that's negative and reflects it above the x-axis. It's just the simplest of examples that we can use for this idea of the absolute value. Let's continue on. I want to get to some more practical application. Okay, so let's do a nice little sketch here of x squared minus 4. This is a quadratic. It opens which direction? Up. And it crosses the y-axis at what number? -4. This is the point 0, -4. All right, this right here would be the point 2, 0. And this right here would be the point -2, 0. Okay, so its domain would be all real numbers. I'm just going to save time, write all real numbers. And its range would be from -4 up to infinity. Now, what would happen to this sketch if I take the absolute value of the entire function? Well, anything that's positive will stay positive. Right? 2, 0, -2, 0. But anything that was negative will now become positive. Okay, you see how it flips over the x-axis there. Let's talk domain on this. Domain? Any change? No, all reals. Range now. Well, if I take the absolute value, that means the least possible value would be 0. So we would have 0 to infinity as our now range for this function. These are interesting graphs. You're not missing much. I'm not going to do this slide. All right, let's talk about the difference here. We kind of did already with the table of values that we talked about earlier. So let's just go ahead and give it a try. Don't discuss with a partner. You don't need to socialize in class. What do you think this is? Okay, let's talk about the absolute value of f of x and f of the absolute value of x. I don't really like this first example, but I like the second example better. So I'm not going to do the first one because they're going to, well, okay, whatever. Parabola opens which way? Down, shifted up, how many? 3, okay. So here is the sketch of the positive portion, and I'm writing the negative portion like such. I don't really care about where these intercepts are, but you might. So -√3, +√3, etc. Blah. You're good. Okay. Now, if I'm to take the absolute value of this entire function, I'm going to take these values down below. I'm going to erase them. Where'd you go? Go away. Go away. Go away. Uh-oh. They went away. And I'm going to reflect them. Oh, that's cool. Sweet. Again, this is -√3, 0, and +√3, 0. Okay, so how would the second one be different? Well, the second one wouldn't be that much different. Right. What would happen to our, let's say, I don't know, -√3, 0. Well, what do we do to the x or the input? Make it positive and then plug it in. Is that going to change at all? Right, I'm taking all of these x values and I'm making them positive. So now -√3, this point -√3 takes on the same output as its +√3 buddy, which is that. What about -1 would take on the same as its positive buddy 1, which would be 2, etc. So this is really just a dumb example because it's going to be the same on both sides because it's symmetrical about the y-axis. Let's look at one that maybe isn't quite so nice. Okay. I want for you, if you're at home, to pause the video and attempt graphing this, at least f of x, and then we're going to do the absolute value of each of those in a moment. Back to our recording, we determined that there's x-intercepts of 3, 0, 1, 0, and -2, 0 in this function. if I take the absolute value of the entire function f of x, I'll do this one in green. Anything that was below the x-axis will now be above. Anything that was above will stay where it was. And look at that. That's kind of cool. All right, now when we do the absolute value of the input, nothing will change for our positive inputs. I'll still have 3, 0 over here and 1, 0 right here. But now that graph will then be horizontally reflected because -1 will now have the same output as +1. And -3 will have the same output as +3. Not my best sketch, but you kind of get the picture. So do the outputs of the negative x values matter? In what sense? Well, if I plug in a -3, do I care what the output of -3 would have been in f of x? Well, now I don't, because -3 now has an output of whatever +3 would be as an input. Okay. So you might still be entering in -3, but before you calculate what the function output would be, before you calculate that, you change that -3 to a +3. Then you input it. And so all of the outputs will match. -3 will match +3. -1 will match +1. -1/2 will match +1/2. And so the graph has horizontal reflectional symmetry. Or we could call it an even function now. I got 3 minutes and 1 second. Let's go. Okay, so what did we say? If we take 1 over what number, it stays the same? 1 over 1 stays the same. Okay, so I'm going to find 1. Here's a value 1, here's a value 1, here's a value 1. If I take 1 over 0, what happens? Becomes an asymptote, undefined. I'm going to have an asymptote here. Why? Because f of x is 0. Have an asymptote here. Why? Because f of x is 0. Have an asymptote here. Why? Because f of x is 0. Okay. Then we said if we have a bigger number and we take 1 over that, it becomes what? Really small. So this big number right here, we'll call it big. This number 4 becomes what? 1 over 4. Boom. This number right here, which I'm going to call, let's say, 1/3, what does that become? 3. Oh, weird. So this portion of the graph will look like this. What? Are you with me? Okay, let's go over to the other side. Right? What will 5 become? 5 becomes 1/5. What will 1/2 become? 2. And 1/2 over here becomes 2. So the sketch of the graph in this region, right, will hit a min value of 1/5. Oops, go back. Right, it has to hit 1. Then it's going to go off to infinity because this value is getting really, 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 really small. Same over here. It's got to go through 1 and then way up like that. Now, what value down here on the bottom half am I missing? Right? We talked about 1 divided by 1 being 1. What else would work? 1 divided by -1 wouldn't change. 1 divided by -1 wouldn't change. And so the sketch of this graph, this function here, well, this is about -2 right here. So 1 over -2 would be about -1/2. And so you'll see that your sketch of your graph will take on that form. So your reciprocal function, let's highlight this in something cool, like, I don't know, orange. Okay, your reciprocal function looks like this. And for those of you who are curious, right, doesn't this kind of look like the sine function, the original one? Its reciprocal is called the cosecant, and it's split up. Oh, it's all, oh my gosh, is it fun? It's a good function.